So we're going to look at real-time dynamic programming. Real-time dynamic programming is a heuristic search algorithm for MDPs, and it's a trial-based algorithm or a sample-based algorithm. So that's how we're going to deal with the probability. Value iteration dealt with probability by enumerating all possible outcomes and then using the transition function to weight the value based on the probability of seeing those states. Right, that's what the Bellman equation says. It says the value for a state is, or the value for a successor state is the value of that state multiplied by the probability of getting to it. That was where we talked about the expectation. So the expectation is like the average taken over all of the probabilistic outcomes, where we weight those outcomes by the probability of actually getting them. That's why we started last week talking about expectation. So the way that a sample-based algorithm does it is instead of enumerating all possible outcomes, listing them and calculating the values for each outcome, we're going to use a sampling approach where we sample from the distribution. So we draw one possible outcome, and a sample is drawing an outcome according to the distribution of that variable. So I sample a dice by rolling the dice. Right? I sample a coin by tossing the coin. Okay, that's a sample process. And computationally, we can do that just using a library in Python or whatever. We write down the distribution and ask it for a sample, and it will give us one back. And if we do that repeatedly, we get the kind of... So RTDP is a trial-based algorithm. So what we're going to do is we're going to effectively grow a search tree from the root to the goal. And we're going to use our heuristic to bias the states we visit. So the idea of the heuristic here is we're using it to tell us which states we should run value iteration for. And the trial-based nature says, well, we don't run value iteration endlessly. We do it once for a particular sample, for a particular outcome. So our trials look like this. We initialize all our state values using our heuristic. So that gives us a good initialization in this case, because we saw from the previous slide that these are actually pretty close to the true values. We start our initial state, so we're assuming our initial state is room D, or state D. Then we need to choose an action, right? So we need to choose an action to apply in this tree. So if you remember breadth first search, what we're going to do is we're going to generate successors by creating applying all of the actions and choosing what to do, which successor we want. But here we're going to just choose one action to apply. That action will be the best action according to the Q value. So this is effectively the greedy policy. Ooh, is there a question there? Sorry, I heard. So we're going to follow the greedy policy. So if you remember, the greedy policy just looks at the Q values locally in a state and takes the best one. So here, best is low because we're minimizing cost. So we compute the Q values, which we're doing down here. And we choose the action which minimizes them. So that's the action of trying to go to E. So we apply that action. Given we've computed a new Q value on the fly, we can back that up to state D, because that tells us something about how good D is. And now we need to generate a successor. So we sample that successor. So that's just like rolling a biased dice or tossing a biased coin. 30% of the time we'd sample D, 70% of the time we sample E. So in this case, let's assume we get E. We only get one of those in the trial, though. That's the trial-based nature or the sample-based nature. And then we do the same again. So we follow the greedy policy. So we compute the Q values for the actions that are applicable in state E. We choose the minimum cost Q value. Again, these aren't the true minimums. We don't know they're the true minimums because we're computing and updating all these values as we go. Okay, and then we reach this until we hit the goal state. So we go to B, choose an action, sample a successor, hit C, and then we terminate the trial. Okay, In this case, I'm being a bit lazy with our sampling and just taking the highest value sample. But in practice, I might have got state D. So that's one trial. And if you look over at the algorithm over here, the way this works and why it's called real-time dynamic programming is that we keep doing this until we run out of time. So as long as we've got time to make a decision, we keep running trials. And this is typically treated as an online algorithm. So what you generally think about is I give my robot 5 seconds to make a decision. And so I let it plan for 5 seconds and then act. Well, sometimes what I might do is as I'm executing my previous action, I start running trials from my successor state. Okay, so trial 2, we sample, we take our initial state, we compute our Q values. So again, E is the best looking action. We sample an outcome. Let's assume we get E again. And then we can run our trial in exactly the same way. And you can see over time in the bottom left, what's happening is we're updating our Q values, our state values. And what I'm doing down here is I'm marking them in bold when they've converged, right? You can see they've converged to the true values down here. But we can use this convergence information. So one of the interesting things about value iteration is it uses this residual, which looks at the difference between values across iterations. And then value iteration terminates when that residual is small. But if you remember when we were running the value iteration example, we actually ran quite a lot of iterations where most of the values didn't change. But in value iteration, you still have to compute values for all states, because typically the way it's implemented runs the maths for all states. But in RTDP, we can actually label individual states as having converged. And that's an extension to the initial algorithm, but it's one that's very commonly used in practice. So what I can do is I can look at my residual, and when my residual between two trials of the algorithm is small, I can label the states. So here, if we look at the kind of thing on the left, the table on the left, we can see that C, the value of C is converged. We can see that the value of B is converged, and we can see that the value of E is converged, right? There was no change in value between two trials through that state. So here, convergence is the same. It's looking at a residual between two updates to your value and checking whether or not the value has changed between those updates. We can see that D has not converged, right? Because the value is still changing. And in labeled RTDP, the advantage of having these labels or these convergence flags is that I can run a trial, but when I hit a labeled state, I can terminate there, because once I've hit a labeled state, I know the values are fixed. So now with labeled RTDP, I don't need to go beyond E in the tree, because the value of E is converged. It's been labeled. That's what the blue circle means. And I can just keep running trials until I hit the labeled part of the tree. And this takes a little while, but then after a while, we converge. And you can see now that if you see down at the bottom, my values for D have converged. And at which point, if I've labeled my initial state, then I know that the algorithm has converged on a solution. And we're using, if you remember, the heuristic to determine that. Right? We don't know at the start which states are likely to be in the optimal policy unless we've used some kind of information. And the heuristic tells us how good those states are. And we only perform backups on the states where necessary. And that's the labeling part. Once those states are converged, we no longer run backups. And we only run backups when we sample new information, so when we run a trial through that state. So these things make RTDP or LRTDP much faster than value iteration. But because it is running value iteration, it is still doing value iteration, just in a sample-based fashion, it's still going to find the optimal policy. So it's an optimal algorithm still, given enough time. And that's quite an interesting property. If I give it infinite time, it will find me the optimal solution. The downside, to some extent, is that because it's a heuristic search algorithm, it only converges to a partial policy. So I can't say anything about the values of the states that I'm not going to visit with the optimal policy. And in general, this is fine. If your model and your world are well behaved, then there's very little argument to say that you need to compute values of those states anyway. But even if you don't have time to compute the optimal policy, you can stop at any point and you will have a policy to execute. So that's one of the nice things. That's the sort of real-time element here, and that's one of the reasons we like this for robotics, is that because it's RTDP, because we can stop at any time, we'll always have an action to execute, even if it's not the optimal action. Although the problem is, with fewer trials, well, with any number of trials, we have no guarantee on how good the action is. So that policy, that partial policy we converge to in sort of short, finite time, could be arbitrarily bad, which is never a nice thing to have to deal with. Okay. There's another sort of subtlety about RTDP, which is generally fine, but is where it kind of comes into sort of focus now as we're transitioning to another sort of set of algorithms. And that is when we do the calculation, when we do this calculation, the Q value, this requires oh, sorry, my handwriting is even worse than normal today. Okay. This requires T, and it enumerates all states. States, actions from S. So in order to minimize over the actions, in order to kind of choose actions according to the greedy policy, we have to do two things. We have to look at all the possible actions, and then we use the transition probabilities to weight their successes. So this has two downsides, and we'll talk about them a little bit more in a minute. One is it requires the transition function in a sort of a closed form or an analytical form. So that's what I mean when I say it requires T. I need to know the probability of S prime given SA. Okay, I need that. And if I've got lots and lots and lots of actions, or potentially lots of successor states, then that can be very computational. The second part can be very computationally intensive. So as an example, Maybe some famous places where these kind of algorithms don't work super well might be poker, right? So if I'm playing poker and I want to write a planning system to plan actions in poker, and I'm playing, say, No Limit Hold'em. And in No Limit Hold'em, I can bet pretty much any size value. And you can think of that action of betting as an action in a Markov decision process. So if I do that, I have to list all possible bets I can make. And then to value that bet, I have to consider all possible things that my opponents could do. And given I don't know what cards they've got, it's very hard to write down a transition function. So something like RTDP works if I've got a model, if I've got a good MDP model or a good transition function written down as probabilities. And it works as long as I haven't got a huge number of actions that could be applicable in an individual state. And that covers quite a large area of single robot planning in relatively straightforward kind of navigation type environments. That's often the case. So this is a good algorithm to know about. And sort of by default, if I was going to use an MDP and solve it for a robot problem, I'd almost always start with LRTDP. It's a simple algorithm, but it scales very well as long as you've got the right information.